Okay, so just to recall, yesterday we proved rectifiability for measures, and the goal for today, for the beginning of the lecture of today, call from yesterday. I'm in depth of showing you the Allard rectifiability theorem. Okay, which, just to remind you, is just saying that if you take a stationary varifold that has almost everywhere positive d-dimensional density, then it's rectifiable. Okay, so if the first variation of the varifold is equal to 0 plus the upper density d-dimensional of the mass of the varifold is positive at v almost every x, then v is rectifiable. Then v is a rectifiable varifold. Where we already clarified what rectifiable varifold means is just, you know, the measure, the space part is a rectifiable measure, and the Grassmannian part, just to remind what we did in the past lecture, agrees with the approximate tangent plane of your rectifiable set. Pretty good. So the only thing that I need to show you for proving this proof by the last theorem of yesterday, of last lecture, I just need to prove that I just need to prove that if I take the blowing up sequence, so actually the blowing up function, because now I'm taking all the radii essentially, it's not gonna depend on the sequence of radii that you choose. Eta xr push forward v is gonna converge weakly in the sense of varifolds to the d-dimensional density of the mass of the varifold at the point x, hd restricted to Sx cross the Dirac delta in the Dirac delta in Sx for some for an Sx that is an element of the d-dimensional Grassmannian. And just as a reminder, this is, and of course this is for v almost every x. Okay? So for v almost every x, there exists an Sx in the d-dimensional Grassmannian such that this convergence is true. Okay, so once we prove this, then we can rely on the rectifiability theorem of yesterday for the mass of the varifold. So this will tell you that the mass of the varifold will be a rectifiable measure. And you will see along the proof, actually, now probably it's not completely clear why this is the Dirac delta in Sx, the Grassmannian part, but you will see at the very end of the proof why in particular the proof itself will give you also the information on the Grassmannian part. Okay, and also at the very end of the proof, we will see also, for instance, a very simple way to see. Remember, there was a question, the first lecture, I think by Emanuele, about this type of object. We will see why each of these plane, in a sense, is creating a sort of invariance for this varifold, which makes this varifold non-stationary. So it will be clear. Now we have all the tools to understand why this is happening, besides doing an appropriate deformation to see this just by computation. We will understand geometrically why that's not possible, okay? So, of course, analytically, you can just do the computation, but geometrically, we will now see it why it's not stationary. Okay, so let's prove this. So first of all, let me start by doing a disintegration. So your varifold V, XS, as we already recalled in the first lecture, you have this classical disintegration theorem for measure on product spaces, can be written as d of the mass of the varifold at the point x times d alpha x. X, notice that here for now depends on x, s. Okay? Now, the first thing that I want to do, since this is a result that I want to show for mass of the varifold almost every point, I will focus on points x0 such that the density, the d-dimensional density of the mass of your varifold at the point x0 is positive. Okay? And this will be true mass of the varifold, weight of the varifold almost everywhere. Okay? And the second requirement. Yeah, because remember we have the monotonicity formula, right? So we proved the monotonicity formula, so we know that in particular the density exists because it's a limit of a monotone quantity. So you know that you can take the limit in the radius, so you can always take the limit. Yes, that's a very good. Yeah, so it's just that yeah, you can yeah, actually there you can put the density. Oops. So yeah, thank you. Okay, and the second requirement that I make is that the map, the x0 is a point approximate continuity for a point of approximate continuity for the map that to x associate alpha x, which is the map that is coming from the disintegration theorem. Okay, what does it mean this? It just means that, actually, said in other ways, this just means that for every phi, for every phi test function, C0 on the Grassmannian of R, the map X0 is of approximate continuity for the map that to X associate the integral phi in the alpha X. Okay? I mean, I don't know if you are familiar with this concept. It just means that, well, let me do a second test. This just means that every time you fix, I don't know, that's epsilon prime positive, the mass of the varifold in BR X0, the weight of the varifold in the set of point X in BR X0, such that the gap between the integral of phi in the alpha X minus the integral of phi in the alpha X0 being bigger than epsilon happens just in a very small measure set, okay? Happens just in a epsilon prime fraction of the weight of the ball. Okay? And again, this is happening almost everywhere, so we can focus to such a point X0. Okay, so I mean, you can do it as an exercise that this happens almost everywhere. You can just choose a dense set of test function and approximate. So you can try to do this as an exercise. Exercise for you. True almost there. Okay, so now let's go to the, yes. Sorry? So this is not depending on the test function. No, wait, sorry. You fix a phi and you can do, sorry. Now I understand the question. Yes, you fix phi and then you do, for every epsilon prime, yeah, you first take phi, then you take epsilon prime, and then you can show this, yes. In any case, it's a localized thing, so you will just, okay. Okay. So, why am I assuming this? Because now, so now if I fix x0 and a sequence of Rj that goes to 0, we will see that this doesn't depend on Rj. Okay, so if I can take the limit, a limit v tilde, as we said, it exists. So this is the limit in J of eta xrj push forward V. Okay, and by the assumption, by this second assumption, the reason I was asking this thing is because I want to disintegrate. So I want to say that this V tilde in particular is the weight of V tilde X cross d alpha x0 S. So what you gain from the second assumption is that since in a proximate continuity point, then when you start rescaling the ball, this is not gonna depend on the Grassmannian measure is not gonna depend from x because it's gonna freeze at x0. Okay, so in particular V tilde as constant Grassmannian part. Okay, so by what we proved yesterday, in particular, yesterday we showed that since V tilde is a blow-up, in particular, I know that Y is in S for every YS in the support of V tilde. This is what we proved yesterday, right? And this is kind of what yesterday we were saying. It resembled a lot to being a cone, because we are saying essentially that if this is the origin, if this is Y, Y should be in S. Okay. Okay, and now I can decompose the support of V tilde. So I can say that in particular Y is in S for every Y in the support of V tilde in the weight measure, and for every S in how I called it, support of alpha x0. Okay, so this is why it's useful to have the Grassmannian part that is constant, because now you can just have this single support measure, this single support of the measure. Okay, but in particular, these two things are implying that the support of the mass of V tilde is contained in S for every S in the support of alpha x0. Okay, so if you now fix one of these S0, fix S0 in the support of alpha x0, so then you are saying essentially that the support of your varifold is entirely contained in S0. Okay? It's entirely contained here. And this is a good information because for stationary varifolds, you can prove it's called constancy theorem. As the name of the theorem suggests, it tells you that essentially your varifold is constant along the plane. So this is an exercise. For you. So since we know that the first variation of the varifold V tilde is equal to 0, and the support of the weight of V tilde is contained in S0, then you can show that the varifold V tilde reads as the density, the d-dimensional density of V tilde at the point 0, which, by the way, I remind you, is the same density of V at the point P. HD restricted to S0 times the Dirac delta in S0. Okay? So the hint for this exercise, so for these problems, if you want to use the first variation, the point is always to use the right test function. And the right test function comes really from the, if you want, imagining that you want to try to solve a minimization problem. So if you have a varifold, if you have an object, a varifold that is contained in S0, but is not a varifold of constant density, what may happen is that you have some region where you have, I don't know, density 2, and some region where you have density 1, for instance, or whatever, some other densities. So what you would expect to increase or decrease the mass of your varifold is just to take a tangential vector field, a vector field that is tangential to S0, because this will, in a sense, enlarge or shrink this kind of region if you were looking at a minimization process. So this is the idea why a good test vector field to use is use X that is C1 compactly supported in S0, in the direction S0, sorry, SRN. Okay, so because this in a sense will tend to may shrink or enlarge region with higher multiplicity, and this will increase the mass at the first order. So this will violate the first variation. Okay, so this vector field, if you compute it, it tells you that you have this constancy. But now you see you have this is true now, but this must be true, is true for every S0 in the de-Grassmannian. Okay, so this is telling you that you should be supported in multiple, in all the D-dimension, sorry, not in the de-Grassmannian, in the support of alpha x0. So this is what we were saying here, what we were saying over there. So in particular, this is telling you that for every element in this support, you should be that entire plane with a fixed density. But then this is telling you that there can be at most one plane. So the plane is unique. So in particular, you deduce that alpha x0 is equal to a single delta on a single plane S0. Okay? And in a sense, now this is what makes it more understandable why, when I was saying in the first lecture, this cannot be, because each of these two lines would determine a direction of invariance, right? So if you were considering H1 restricted to a line, and then you put in the Grassmannian part, I don't know, 1/2 of the Dirac delta on L1 plus 1/2 the Dirac delta in L2, you would see that in a sense, by this computation, each of these two lines will give a direction of invariance for your constancy theorem. And so this would force your varifold to stay on both these lines. And this is a contradiction with this computation. So this is why this guy cannot be stationary. Okay, so in particular, since alpha x0 is equal to the delta in S0, this concludes the proof of our rectifiability theorem. Any question about this? Okay, so if not, so let's see how this rectifiability theorem gives me a result that is very useful in the min-max theory, that is the compactness uh, for integral varifolds. Let's say for rectifiable varifold first. Yes. So that's, yeah, so that's you, yeah, you're right. So that you can show it by the assumption that we made on the density. So you can show that the weight of V tilde, so when you blow up V, the limit of the limit of the blowing up sequence of the weights of V converge to the weight of V tilde. So in particular, you deduce that the weight of V blows up to theta D mass V tilde 0, HD restricted to S0, yes. And then you use the theorem we proved yesterday for the mass of V tilde. But this is what I was saying. So in the theorem is not immediately clear then why you get also the Dirac delta in S0, and this is because of this computation. This is the extra computation that then fixes also the Grassmannian part. Thanks for the comment. Okay, so compactness for rectifiable varifolds. Mhm. So you can show that if I give you given Vj, that is a sequence of rectifiable varifolds, D dimension rectifiable D varifold. Okay, which have this is important, have a lower bound on the density. Okay, so the D-dimensional upper density of mass of Vj at any point P x is bigger or equal than theta 0 for Vj almost every x. I'm calling it x, yes, for Vj almost every x. So I have a uniform lower bound on the upper density, and on top of that, I know that the supremum of the weight of Vj in a compact set kappa is finite in J, and the supremum of the total variation of the first variation of Vj kappa is finite. And for now, this is what you can do in general, but in this, since we are proving everything for first variation equal to 0, let's say dvj is equal to 0, but you can do in this generality, and this is true for every compact kappa, for every k compacts in Rn. Okay. Then there exists then up to subsequences, Vj converge to a limiting varifold V, up to subsequence. Up to subsequences, and the varifold V, and the varifold V satisfies the same lower density bound. V rectifiable, and okay, V x bigger or equal than theta 0. It's important that this theta 0 doesn't depend on j. Independent on j. It's bigger or equal than theta 0. And the, let's say, proof sketch, let's say more proof hint. We're not gonna, because we don't have much time. The idea is that you have to combine the upper semi-continuity that we saw yesterday, apply. So first of all, you know that this information, as we saw yesterday, just by weak star convergence guarantees that you have existence of a limit. So apply upper semi-continuity we saw yesterday to get lower density bound on V, okay, by the idea of yesterday. And now you apply the rectifiability theorem. Apply the rectifiability theorem to conclude that your limiting varifold is also rectifiable. Okay, so this is the two ideas. I'm emphasizing this because there are more general contexts that we will see a bit later, where, yeah, if you don't have upper semi-continuity of the density, then even if you have a rectifiability theorem, you don't get compactness for integral varifolds. So in this more general context, this is what prevents to do, for instance, Allen-Cahn for critical points of these energies. Okay. As a corollary, in particular, you get the compactness for integral varifolds because you can choose just theta 0 to be 1. Well, and you should be a bit more precise because also you want to show that almost everywhere the limiting density is integer. But let's say a corollary of this. Corollary, you also get, as this is the compactness for rectifiable varifold, you get the same result for integral varifolds. For compactness for integral varifolds. Okay, so this is really just a consequence of what I wrote above. You just have to have the assumption of integer density, integer value density. Okay, so this is concluding a bit the structural property of varifold for lower order structural property for varifolds. Now, in order to say something about the higher order regularity, like C1 alpha Allard type regularity theorem, we need to understand a bit better the blow-ups of stationary varifolds. So now I want to say something more about tangent cones. So as the name suggests, we will show that essentially, as we were understanding already in the past lecture, blow up looked a lot like cones in their property. So we had this property that ys every ys in the support of your varifold satisfy the property that y belongs to s, right? But in general, this doesn't mean that the varifold is scale invariant. So this is something that you have to show in a sense, right? So let's see this kind of property. And so the proposition that I want to show you, because it's kind of useful in the this is one of the reasons why the regularity theory for the area is so much better than other type of energy. the another type of energies is if you consider a varifold, V be integral varifold, okay, and say that it has zero first variation, so it's stationary, and now you fix a blow up W, fix W, a blow up of V, of the varifold V, then V is a cone, then W is a cone, is a cone. Which just means that, as we were discussing yesterday, W is radially invariant. So if you take um, if you take eta 0 rho, push forward your W, you get again W. Okay? So this is what we want to show. So notice that here I'm assuming V to have to be an integral varifold, because essentially I use the compactness for integral varifold. You can do the same with using the compactness for the rectifiable varifold that we showed. However, remark, it's an open question, I think, in the field. So it seems a very basic thing to prove. So it seems like a result of measure theory, but it's an open question to show if this is true without the positive density assumption. So are blow-ups cones without assuming that the density of the varifold is positive at almost every point. Okay. The density of the limiting blow-up is positive at almost every point, because in principle, you don't know the rectifiability, and the problem of not knowing the rectifiability of W is that then we cannot very well relate. You will see now in the proof, we cannot really well relate the Grassmannian part with the space part of your varifold. So this is still open, although it seems something really like a measure theoretic question. So it seems very elementary, but it's not known. So let's prove this. And indeed, the starting point that helps me is that proof. Why am I saying that is open? Because indeed, the first thing that I do is that, well, since W is a blow-up of an integral varifold, is a sequence of integral varifolds that are stationary. By monotonicity, it has a uniform bound on the mass locally. So in particular, I can apply the compactness for integral varifolds. So by previous theorem, W is integral varifold. Integral varifold, and not the important thing is not just that it's integral, is that it's rectifiable. It's integral varifold. Well, and of course, it's stationary. Okay? So in particular, since a rectifiable varifold is just described by, by the weight of the varifold, I just need to prove that the weight of the varifold is a cone. Okay, I don't need to show anything about the Grassmannian part because that will just follow the space component. Okay, so I just want to show, so the only claim is that if I take eta 0 rho, push forward W, and I take the weight of this guy, then this is just the weight of W. Okay, so I just care of studying, so for every rho this. So I just want to show that by test function, I just want to show that for every key, test function chi in C1 compactly supported in Rn, the integral in Rn of chi in d eta 0 rho push forward W is equal to the integral of chi in dW. All right. Okay, so now I want to show the dilation are behaving like, so it's invariant under dilation essentially. So let me, and I also want to use the property that this is stationary. So let me use that. I need to use an appropriate, let's say, variation that I can use to apply that the first variation is 0. So let's, to this aim, let's choose as a vector field x of x just equal to x, the radial vector field, and let's choose a one parameter family of diffeo such that it's quite regular. So phi tx, for instance, we can take e power t capital X. And with this change, you can just so this is, of course, generated by capital X. And now if you compute the derivative in rho at rho equal to e power t of the quantity we want to prove that essentially is constant in rho. Okay, so this is the integral in Rn of chi d eta 0 rho push forward W. Well, you can see as an exercise that this is just the derivative in t up to the change of variable. So that is, you are changing a bit the speed. So it's e power negative t, because this is, now you are using phi t. So this is the derivative in t. The derivative in t of the integral in Rn of chi in d phi t x push forward W. Okay. So now the idea is that I want to use this to compute, to impose that the first variation of my W is 0 along this type of deformation. I cannot yet use this because it should be also compactly supported. So let me do a small change. So first of all, you can make this computation, and this is just by expanding the definition of the push forward of a varifold. So using the definition of push forward and computing the derivative, this is just so if I compute that derivative at let's say t equals 0, so that you have exactly rho equal 1, you get e power 0 dt is 1, and then you get the integral in Rn. You have first the gradient of chi, scalar product with x, plus then you have chi, scalar product with the gradient of the vector field that is x, times scalar inner product with the tangent plane that is Sx in the mass of the varifold. Okay, so for this computation, you just need to expand the push forward of your varifold using the formula of push forward and then take the derivative. So, and you will see that the t will happen both in chi and x, so you have to take the derivative of both. It's product rule. Okay, so I cannot use here the first variation to conclude that this quantity is 0. So I would like to conclude that this guy is 0. I cannot do it immediately. So let me take another vector field. So let's fix x tilde, that is a new vector field that is defined by as chi times x. Okay, and now let's compute what is the first variation of w at x tilde. So remember that this is just the gradient of x tilde, scalar product with Sx. This is just by the definition of first variation we saw yesterday, against the varifold w. Against the weight of the varifold w. But now the gradient of x tilde times Sx, this guy is what? Is gradient chi tensor x inner product with Sx plus, I put a bit up so that you can see, plus chi gradient x Sx. Okay? And also remember that this guy now is 0. Okay? Now I just want to observe that these two quantities are the same. This guy is the same as this guy. Why? Well, this is already the same. And about this guy, why are these the same? Because why are these two terms equal? Oh. Yeah, for stationary varifolds, it's not known whether you can prove that the blow-up is a cone without assuming that the blow-up has positive density, yes. In a sense, what we miss is the first step when I say I just care of the space part. Let's look at this guy. Gradient chi tensor x scalar product with S. This is just, if you want, you have to saturate S of x on both these two guys. But since they will both live in Sx, you can just saturate it on one of them. So you can just do, for instance, I conveniently choose x, the one to kill S of x, scalar product with gradient of chi. And why I choose x? Because remember, we proved that since capital X is equal to little x, we proved that x belongs in S of x for mass of varifold almost every x. Okay, so this guy almost everywhere is actually just capital X. Okay, so in particular, what we showed is that this guy is capital X gradient chi, which is exactly this guy, and so this guy is 0. So we showed just that this term, if you want at equal 0, or if you want that derivative at rho equal 1, is 0. But now you can iterate this, you can make exactly the same proof on a dilation of W. So you can repeat this proof. You can repeat this proof. So you can repeat this proof for eta 0, let's say e power t push forward W. You can do exactly the same proof, and you would deduce that then the derivative in rho is not equal to 0 just at rho equal to 1, but now you will compose it with this extra e power t. So you will know that the derivative of in rho of that integral in Rn chi di eta 0 rho push forward W is equal to 0 for every rho. And in particular, you deduce that what you wanted, so W is a cone. Okay. And this concludes the proof. So in a sense, it's true that the property we deduce that ys is, so y is in S for every couple ys in the support of your varifold makes us think that is a cone, but you actually then need to show that the mass, the weight of the varifold behaves accordingly. And the Grassmannian part will follow the weight just by the fact that it's a rectifiable object. Yes? Well, because remember what, so you want to show that when you do a deformation, the Grassmannian part should also agree with the new. So you take your set, you dilate it. Now in the dilation, the Grassmannian will be will be changing kind of the differential of the former tangent planes. But now you need to know that this stays fixed. That's the thing, right? You don't know in general that when you do the push forward, then the Grassmannian, so the Grassmannian part will be invariant in a sense. So you don't know how to show. So this is, I think, what is missing, how to show that the Grassmannian part is invariant. So here it comes automatically from the fact that essentially the Grassmannian already agrees with the dilation. So, but for a general varifold that is just stationary, how do you know that when you apply the dilation, you go in this other point and in the dilation, the Grassmannian part stays the same? Like the differential, in principle, the differential doesn't change this guy because the differential applied to S is S itself. But if it's something else, the differential can change the planes, right? So you don't know in general. So the differential can change the plane. So you don't know in general that when you dilate, the Grassmannian is, in a sense, kind of zero homogeneous. Like, yeah. So it's homogeneous. Like it is preserved along the dilation. So that's I think what is missing for the, if you don't know a priori that the limit is rectifiable. Okay, so about this, the fact that cones are tangent, I just want to observe a nice property out of this. That is, we can call it cone splitting. Just a remark, but I think it's useful when you do, for instance, reduction argument or you go in the regularity theory. Cone splitting. So if I fix a varifold W that is blow up of V at some point, of V that is stationary, integral. Okay, so the observation that we want to make is that assume that there exists an x hat, another point different from 0, such that the density at x hat is exactly the same as the density of the blow up at the origin. Is the same as the density of the blow up at the origin. Okay. What do we deduce from this? So remember, we made a small exercise. That's the exercise we did together yesterday, where we showed that at any other point, so I conveniently did it yesterday for today, to have this for today, that this is always bounded. The left-hand side is always bounded by the density ratio at every scale, by monotonicity. And this guy is bounded by this guy. Okay, here the proof was slightly required a little argument. It was just the same argument that you need for upper semi-continuity. This slightly enlarging of balls. So in particular, what you deduce, since this has to be true for every R, you deduce, and we are assuming that these two quantities are the same, you make the monotonicity formula being saturated at every scale, right? So monotonicity formula is saturated at every scale. So monotonicity formula for W at X hat is saturated at all scales. But what did we deduce from the fact that the monotonicity formula holds with an equality at all scales among the two density ratio? We deduced that the property that the gradient on the orthogonal of the tangent plane of the norm of X essentially is equal to 0, right? So this is what we used to show that X is in S of X. But now we can do this same property at X hat. So we also know that X minus X hat is in Sx, right? Because now the center is X hat, right? But for the same argument that we did yesterday. This is the same argument, it's just that you are doing it at the point at the center X hat. Okay, so in particular, if this is in Sx, And this is in Sx, in particular also x hat is in Sx. Now, let me do a picture of what's going on, because otherwise it's just symbols. Our friend stationary varifolds here. What I'm saying is that yesterday, we remember we were saying, if this is your point x, the multiplicity here is different from the multiplicity here, because here is 1/2 and here is 3/2 the density. And as you enlarge, it's not a constant, because at some point you hit this line and it jumps a bit higher. It starts jumping a bit higher. But, and where this is the origin. But if you take a point x hat that is here, you see this is just translation invariant in this cylindrical direction. So at this point, the density is exactly the same as this point. And indeed, what is happening is that for every x you select, also x hat is in the tangent plane. So indeed, x hat is in both this plane, is also in this tangent plane, and is also in this tangent plane. You see, this line here is the intersection of all these tangent planes. Okay? So this is the idea of cone splitting. We are basically seeing that all points in this x hat that satisfy that property, which have same density of the origin, generates a line of splitting for the cone. Okay? So in particular, we are saying that W can read as R times W prime, where R here is exactly in the direction of x hat. Okay, is generated by x hat. So now if you will pick other x at prime, an x prime that is on the same line, you will not get new information. But in principle, if you find another point, x second, which is another direction, you will now have a splitting of order 2. And you can stratify your splitting with this, with the understanding of which point have the same density of the origin. Okay? So, and where this W prime will be again stationary and integral cone. And integral cone. And this is at the base of, it's a very simple observation, but for instance, when you do, when you have to show like regularity for area minimizing, or for like, for instance, if you have to show compactness of stable hypersurfaces, you take the limit, it's basically understanding the blow up, doing this cone splitting and understanding whether at which dimension this splitting can happen, essentially, by using the stability. So then you have to use a lot of techniques, but what I'm saying is that this simple observation is very useful then when you go to prove regularity theory for stable, already for energy minimizers, but even for like when you do the compactness for stable hypersurfaces, for instance, in the work of Shen-Simon, this is used in the paper of Almgren Shen-Simon for the anisotropic energy minimizers. This kind of idea is used. Okay. Any question about this splitting? Yeah, S of x. S of x for me, once we have assumed that varifold rectifiable, for me denotes just the mass weight of W almost everywhere tangent plane of x. So almost everywhere you can associate to x S of x. This is the, remember, this is what we proved by the fact that W, so this is W. Remember, yesterday we showed that if W is stationary, so let me repeat. Maybe it's good to see it again because now you see the use of this. Remember when we had the monotonicity formula? So when we had the monotonicity formula, we were showing that by the monotonicity, how are we writing? So we first showed this yesterday, that the density at the blow-up point, if you fix the blow-up point, that here becomes the origin, this point was saturating the monotonicity formula. We proved that just at the origin, it's always true that this is this guy. This is what we showed yesterday, the first thing. Then we remember that there is a monotonicity formula that tells you that if these guys are equal at all scale, there is an error term in the monotonicity formula that is this. The integral on the Grassmannian bundle of B capital R 0 minus B small r 0. These are the two radii that I'm using for the monotonicity formula of the gradient of S. In this case, I can already write X orthogonal of X minus 0 square over X power T, right? And this is in the mass of the varifold. And this was 0 because this is the error term in the monotonicity formula. This was telling us that S orthogonal at the point X of the gradient of the norm of X is equal to 0. Exactly. So this becomes exactly Sx orthogonal of X over norm of X, which is 0. But if the projection is 0, it tells you that this is exactly in S of X. X is in S of X. And this is how we showed this yesterday. So this is what we proved yesterday. I'm just making now an extra observation and saying, look, since I'm assuming that the density at X hat is the same of the density at 0, the same saturation and yesterday I also proved for you this guy, but that argument that also gives the upper semi-continuity, it was the last exercise I think we did together. I showed for you this, but then this means that this is also saturating the monotonicity formula as in this case, but now at the point X hat. So here, the only thing that will change is that you have to do this. You put an X hat here, an X hat here, an X hat here, and here would be X minus X hat. And here would be X minus X hat, X minus X hat, and this is 0. And so now we have that X minus X hat is in S of X. Yeah, thanks for the comment. So we know that this is in Sx, and now we have this. And so this is why this X hat splits a line in your tangent cone. And now the more direction, let's say, of same multiplicity you find, the more direction of invariance, the more cylindrical, sorry, not, direction of invariance, or if you want them, the more cylindrical direction you find. Any other question about this? And it's a good thing to observe because this is a kind of an observation that makes you understand why in Allard the regularity theorem that we state in a second, a flatness assumption becomes just an assumption on the mass, essentially. Because by this kind of idea, we are not going to go into details, but heuristically, we see in a second that a mass assumption becomes a flatness assumption. Any other question? Okay. Okay, and indeed, the last thing that I want to discuss before adding a bit more jets to the lecture is the higher order regularity. Regularity. For stationary varifolds. Okay, so I have a stationary varifold, let's say integral, so that we are in a good situation. Already you immediately tell me, well, there is a regularity that I cannot beat, that it's what at most you could be able to prove. Because you see, remember, two planes that are crossing are stationary. This is like a super well-behaved varifold. This is actually integral almost everywhere with multiplicity density 1. So there is not much you can do. This has multiplicity 2 and this has multiplicity 1 point. So the best you could hope for is that the singular set, the dimension, if you want, the codimension of the singular set is, if you want, 1 in the varifold, in D. Okay? So you cannot hope for much more. Oh, okay. I mean, I'm writing it in a terrible way. So you cannot hope to do more than dimension of the singular set less or equal than D minus 1. This is like the dream goal. More than this, you cannot. But this, we are kind of very far from this kind of result. There is not much in this direction. So literature. So this is the guess. This is the conjecture. This is what many people conjecture. So some people conjecture. But we are very far from this. In fact, we don't know much more than just stationary varifold. We don't have much more information than just this theorem that I'm stating of Allard, that is of some decades ago. The 70s, let me write. I think 71 probably, paper. 72, huh? Okay. Okay, so this is a regularity theorem at point of density 1 that tells you the following. For every dimension, n in capital N, you will find a little constant, a constant that depends on n, positive, such that if you have a stationary integral varifold, if the varifold is stationary, well, d-dimensional varifold, and integral, I could have written in the adjective goes first, integral d varifold, and you take a point x in the support of the mass of the varifold, of the weight of the varifold, sorry, such that for some ball R, the mass of V in BXR is less or equal than 1 plus Cn of omega drd, so the area of the d-dimensional disk, then the varifold V restricted to the Grassmannian bundle in the ball of radius half is a graph with multiplicity 1, is a smooth graph. And in particular, and also with multiplicity 1. Okay? So this is actually, for stationary varifold, you cannot do much more than this. Sorry? What is what? N? No, all these one, it's just my bad handwriting. All these are all N. So N is the dimension of the ambient space, Rn. I don't know if this was your question. So which one? So all these guys are all N, are all the same. Sorry, it's just me that I don't have a good distinction. Yeah, like for me, N is this. So these are all N. And I guess, and here. They're all the same number. So yeah, this is in all this talk, we are always in for, until I say in next lecture, I change it. So we are always working in the whole lecture. We are always working in Rn. Yes. This is our ambient space. Okay, so this is what you can say. And I just want to discuss briefly this result. So we will not prove this because otherwise I can, yeah, so it will take too many hours and we still have to go to the min-max. I just want to discuss something. So the first thing that I want to discuss is that once you say that the point X is in the support of your varifolds, in a sense you are saying already that the density is bigger or equal than 1 because it's an integral varifold and you have upper semi-continuity. But the other, a couple of other observations, when I say that the varifold is a smooth graph in that ball, it means that there exists a function f from S to S orthogonal, such that the varifold restricted to this Grassmannian bundle BR alpha X is basically the varifold generated by the graph of F with multiplicity 1. This is the meaning of that statement. And also, one last comment that I want to make is actually you can add a bit more control on that result, in the meaning that so you can make, if you want, also that with you can make an F with a norm that is as small as you like, in the meaning that remark you can actually prove, show that for every integer and epsilon positive, there exists a delta, which now depends not just on n, but depends also on the order that you like of regularity and on epsilon, such that if the mass of your varifold in the ball of radius r x is less or equal than 1 plus delta omega drt, then actually you can bound the CL norm by epsilon. So you can now, of course, the difficult part is to prove that F is C1 alpha, because then you can bootstrap by using the fact that this is an actual graph, and then you just use standard elliptic theory to bootstrap to higher order. Just in this case, the mean curvature is 0, so the right-hand side is 0, so it's very easy. The other observation that I want to make is that why these results should be true. The proof is based on improvement of flatness. On improvement of flatness. of flatness. And why this improvement of flatness should be true? Because imagine that your varifold V was already smooth. Okay, let's imagine it as a sort of a priori estimate. Imagine W is smooth. Okay, then F would satisfy the graph of W, and let's say codimension 1. Codimension 1. W would be described by the function F, which would satisfy then the minimal surface equation, right? So the divergence. So probably I'm saying here something that you have already all seen, so I don't know. But if, yeah, let me say it anyway, because I think it's good to say it once. The minimal surface equation is the divergence of the gradient of F plus 1 over the norm square of gradient F, okay, equal to 0. But now you want to do an improvement of flatness. So if at some point you can show that the gradient of F is very small, okay, so this is what you do in the proof. You show that some smallness of the gradient of F. So if this is very small, then the whole denominator here is close to 1. So this is close to say that to be harmonic. And for harmonic function, you have improvement of flatness. Okay, so probably I'm sure that you have already seen this kind of heuristic other times, but let's say it once. Okay, so in the last, I have 3 minutes. So I just say what are the steps. So we are not gonna go into the proof. Just let me say the steps. So the first step is a proof of flatness in a measure and in an Hausdorff sense. And I want to say just also this just because to see why that heuristic on the splitting of the cones is useful. So say proof idea. So set X the point at which you are doing the regularity equal to 0. The first step is flatness in measure and Hausdorff. Because you see, saying that in a ball, since your varifold is integral, saying that in a ball your density must be very close, the density ratio should be very close to 1, essentially is forcing the points all to have density very close, density ratio very close to the density ratio at 0. So in a sense, they are not all cone splitting, but they are all almost cone splitting, right? So they are all forcing your varifold to be very flat in a measured sense, of course. So by the ideas of the cone splitting, in measured sense, your varifold is close to be flat. So this is your, I don't know, S, and your varifold will be very close to this. But in principle, there may be some spikes, okay, that you don't see in a measured theoretic sense. The reason why you can remove the spikes is by the fact that you have positive density and you have a monotonicity formula. So you pick one of these points in the spike, you take a little ball around this point, and this by the assumption on the fact that the density is positive and the monotonicity formula is telling that this has to carry at least a density ratio that is equal to the density at this point, okay? That is integer, okay? So this is telling you that this carries some mass, so this cannot happen. So this guy is not there. So a measure closeness imply a measure flatness for the area implies a C0 flatness, implies a closeness in Hausdorff. So you deduce, in a sense, a C0 flatness. And I think I need to stop here, right? So this is the first step, but yeah. So we were not going to discuss much about the proof. Maybe next time I just start by saying very briefly that, and then we move forward. So tomorrow. Yeah. Thank you very much.
Questions? Remarks?
So I think we saw yesterday that we proved that on the cone, on the blow up, the density is on any point is smaller than the density on the vertex, right?
Yes. Yes.
Okay. But doesn't this imply some or also that so that we only get some type of cones? Because for example, if I imagine some maybe thin cones, something like that, the density at the vertex is smaller. So do we from that property do we get already immediately something that's only some type of cones arise
So by
or is it I don't know.
yeah,
Because up to now we just said that the blow is some cone, right?
yeah.
So we didn't say anything. So
No, no.
from that can we deduce something?
Yeah. So for instance, for sure you can exclude something. So knowing that the density, for instance, if you know that the density has to be, for instance, bigger or equal than one, we are integral varifolds, and the density has to be bigger or equal than one, then in particular, yes, you can exclude just by a mass ratio computation, you can exclude some types of cone. But in a sense, even if you exclude cones that are putting very little mass in a ball, like, as you are saying, if you take very tiny cubes that counts have an epsilon mass, still understanding in general what are the blow-ups is very difficult because even, so yeah, even if you have polyhedral cones, the combinatoric can be as big as you like. So I agree that you can exclude some cases, the cases that carry very little mass because of a density assumption, but still you will, you have a lot of possibilities. So in practical, you cannot really characterize the stationary cones. Yes. Thanks for the comment.
Other questions?
I did not understand completely the cone splitting idea. Like, so if we have a point with maximum density, then it belongs to the tangent to any other point.
Exactly.
So how does this imply some?
So, well, I mean, I have to say it was not, so this was just an idea, an idea. It was not a formal proof, but heuristically, so this, by the way, if you have the origin and you have this x hat, all the other point in this line will satisfy the same property.
Yes.
So you are saying that to all this line should belong, so you have this line in this, let's imagine it as a support. You have a line that belongs to all the tangent planes of your to all the tangent planes of your support. So this is not a proof, but the way you can imagine it is, so that's all these conical tangents all have to intersect with this line. So you have, this line should be, if you want, this line is an intersection of all the, so for sure this implies that this line is the intersection of all S of X. Let's say this is in a measure theoretic sense because it's almost everywhere. So let me put it like this. But X is in your cone C. Oh, let's call it C. So in particular, this can be just, in a sense, a book, right? So it can be a line with all this, with this plane opening. So this tells you in particular that along this line, your cone is cylindrical, right? Because all these planes here will be cylindrical. All this cone will be cylindrical in L. And also we are using the fact that it's a cone. So the fact that that's a tangent is a property that you preserve along the radial direction. So this will be preserved. If it's true here, it will be true also along all this. This will be the same tangent in all this point. So this is why then it becomes cylindrical in the direction of L.
Okay. And how do you use, I mean, how does this apply to our flatness measure?
Oh, this is even more like, this is really a computation. It's not a cone splitting. Here I just wanted to make a similarity, because here we use that the monotonicity formula is exactly saturated, right? So it's the density ratio at R is equal to density ratio at small r. You can imagine that if you have that assumption, the monotonicity formula is not in general saturated, but it has very little room of wiggling, right? So you have to imagine that now we have to make a quantitative argument. So it becomes not a qualitative rigid argument, it becomes quantitative. So you say, well, that error term, that is the integral of the gradient of S orthogonal now, will be bounded by this little gap that you may have delta. And that little gap tells you how much you can be far away from being the plane. Because if you had too much of a gap, then you will start having, if you would be too much far, then you would start having density that drops too much. So this will tell you how close you have to be measured to the plane. And then, yeah, the C0 closeness instead is just monotonicity formula, because the monotonicity formula tells you that a point of positive density carries a definite uniform amount of weight. So it's a quantization of mass, essentially. And so it cannot happen to be outside of a Hausdorff topology strip, metric strip, close to us.
Okay. Thank you.
Thanks for the comment. Right.
I just had a quick question on how are you able to extend the compactness for rectifiable varifolds to integral ones? Because I thought you were just sort of getting a lower bound on the density. So how are you able to prove then that it's an integer?
Yes. So this is indeed this is a bit more subtle in the meaning that one thing that you have to do. So the fact that it's you get a density lower bound is clear. One extra step that I didn't say is the following: that you first get the rectifiability out of the compactness for rectifiable varifold for the limiting varifold. Then there is an extra lemma that you have to add that I didn't have time to go through, is that now you take almost every point of this limiting rectifiable varifold. This will be a plane. So almost every point will be a plane. And now you take the sequence of varifolds that is approximating in the limit this plane. So you have the sequence. So up to a blow up, you can imagine that your limiting varifold up to a diagonal up to a diagonal argument, you can assume that your limiting varifold is this plane with the constant density. And the approximating sequence for which you want to make convergence is this sequence Vj. That is, if you want the blowing up sequence applied to the sequence Vj by a diagonal argument. And now what you want to show here, this is a technical thing that we didn't have time to do, is that you want to show that this doesn't converge just in the measure sense, but it converges strongly. So it converges in total variation, actually. So you can show that, I will say something about this maybe tomorrow in a more general setting, but you want to show that if you take, let's call this plane T, or S usually we call the plane. If you take S, push forward this varifold Vj, they converge in total variation to a constant. So minus H gamma HD restricted to S. This in total variation, let's say in Bt, in every ball of radius T is converging to 0 for every T. And this is, you can show this for the area functional, you can show it again using the monotonicity formula. In more general context, there is this other way of proving this that is called the strong constancy lemma, that instead is based more on an harmonic analysis argument. But yeah, we don't have time to go too much into these details. But you are totally right. There is an extra step to do that we didn't have time to cover.
All right, thank you.
You're welcome.
Okay, so if there are no other questions, we thank again.
Thank you.
Antonio?
So let me start with the thing maybe I should close the window here. A lot of noise. So I start with the definition of octagon housing circle. A optimal Hausdorff oracle. I said if there are two things. First of all, it should be a Hausdorff oracle. And also, for every other oracle, for every oracle B, and for every epsilon, there is an X such that when you look at the complexity of X using both A and B, so this should be at least, X is of course an E, it should be at least the Hausdorff dimension of E minus epsilon. So this we can always do. Remember, I discussed this a lot yesterday. So for every oracle, in particular for the pair of oracles A and B, you can always find a point whose dimension is close to the dimension of E. But now I will, so this is always okay. But now I require more. So this and for every scale, every large enough scale n, for every large enough n, I want that the complexity on that scale using both oracles is larger than the complexity using only A minus epsilon n. So here's a picture. So say this is n, this is k and x. And I have two lines, the line with the slope of the Hausdorff dimension of E and the line with the slope of the packing dimension of E. And without B, so just K and A, it does something. Eventually it stays between these two lines. Maybe it oscillates. I mean, it should be a monotone function. I'm sorry, in the picture it doesn't look like a monotone function, but I was trying to say it goes between the Hausdorff and the packing dimension. So this is K and AX. And now I want that K and ABX is somehow, it can drop, but it cannot drop too much. So it's just three pitches wider and wider, but only by some small epsilon, and it should be so K and A comma BX should be somewhere, at least for every large enough scale, it should be somewhere inside this strip. So I hope it's obvious from this picture that if the Hausdorff dimension of E is the same as the packing dimension of E, so in that special case, everything is trivial, because both of these curves will be eventually very close to this line, which is the Hausdorff and the packing dimension, and then of course what we want is true. So this is a trivial remark. If the dimension Hausdorff and the packing dimension of E is the same, then just every Hausdorff oracle is an optimal Hausdorff oracle. Every Hausdorff oracle A is optimal. So this is really an interesting notion when they are different. But this remark also says that this is not only about analytic sets. So So of course, there are lots of sets which are not analytic, but they have the same Hausdorff unpacking dimension, and then they do have optimal occurs, and then we expect that everything in geometric measure theory is true for those sets. So it's not just another way of saying that everything is true for analytic sets. Somehow these proofs all give something new compared to classical results, because they also show a set has the same Hausdorff unpacking dimension, then the classical statement is true. So what really the meaning of this picture is that we can, so let's try to say this in words. So A is an optimal oracle if for every other optimal, any other oracle B, you can find an X such that B cannot give too much new information on X, only very little. So A was already giving some information on X, and B may tell something more, but almost nothing. So for A is an optimal oracle, it has this property. For every other oracle B, there is a point that B doesn't have that point. Knowing A is really almost the same as knowing A and B. That's what an optimal oracle is. So are there any questions so far? Okay, so once you have the definition, some trivial properties. So these things are easy. Follows easily from the definition. So the first one is that if you have a subset of E and F has full dimension, same dimension of F as E, and F has an optimal oracle, and E has an optimal oracle. So this really follows immediately from the definition. And another thing that follows with very little work from the definition is that if we have countable many sets inside, we have countable many sets with optimal oracles. Then their union also has an optimal oracle. So I won't show you this. If you look at the definition, you should be able to see it quickly. And now the theorem that Don proved, or at least a special case of his theorem, is that if E has positive and finite S-dimensional measure for some S, then E has optimal oracle. So that's really the key result. These are easy, this is less easy. And once you know all these three, it's a corollary that every analytic set has an optimal oracle. So this is really just the Borel regularity of the S-dimensional Hausdorff measure. Inside every analytic set, you can find a Borel set of the same dimension. And then inside that Borel set, you can find sets of positive and finite measure, maybe not with the same dimension, but you can have a sequence of SNs converging to the dimension of your Borel set. And for each SN, you have an SN set, and then the union will be a set of full dimension, which has an oracle, and therefore the analytic set has a good oracle. So really the key thing is to understand this theorem. Why is it true that if I have a set E, which is an S set, so there is for some S, its measure is positive and finite, then it always has an optimal oracle. And this looks hard. Somehow the main reason why this looks hard is that So of course, we are trying to do this using complexities. And I explained you in the last lectures how we can find the dimension of a set using complexities. But this is something much more delicate. We don't just want to find the dimension of the set, but we are trying to understand which sets have positive and finite measure, and we try to do this using oracles. So for those of you who have a little experience about working with Hausdorff measure, the upper estimate is usually not so bad. So to show that the Hausdorff measure of a set is bounded by something, you just need to find a good covering that shows that it's bounded by something. But the lower estimate is usually much more tricky, because then you have to do more. It's not enough just to find one covering. So really the first question we should ask ourselves, how can we understand? How can we see if a set has, whether a set has positive measure, not just as dimension, but positive measure using oracles. So we know how to see the dimension of a set, but how can we distinguish between zero measure and positive measure? So the answer to this is that we do something a little bit different than what I explained in the last two lectures. So instead of Kolmogorov complexities, we use something which is just a little different. So we use what is called prefix free. Thanks. Prefix free Kolmogorov complexities. Which is, maybe this sounds intimidating, but it's something extremely simple. So what I mean by prefix free is, so I show you in the first lecture two different definitions of Kolmogorov complexity. So if I use my heuristic definition, so kx, this was the length of the shortest sentence, encoded in zeros and ones, finding x. So the only extra rule I add to this is that it's really a sentence. I cannot have more than one sentence. So this will be that x is the point, or x is the finite sequence of zeros and ones with this property and this property and this property and this property. I always put an and between, and the important thing is that the sentence finishes by a period, a dot. There is an end of the sentence, and then I cannot start a new sentence. Or if you think in the term of algorithms, so kx is the length of the shortest algorithm, then and the extra condition I add is that every algorithm finishes, the description of every algorithm finishes by saying this is the end of the definition. So you put an end at the end, and that's really the only difference. And I hope we agree that this is harmless. So the reason I didn't tell you before that Kolmogorov complexities are prefix free, because it didn't play any role. It didn't matter which one we used. But actually, if you want to understand whether a set has positive or finite measure, it's much easier to use prefix free complexity. So the way I like to think about this is what this really means. So I have all these finite sequences of zeros and ones, and I can just draw it as a binary tree. 0, 1, 1, 0, 1, 1. And so on. And in this tree, some of the nodes, some of the vertices are valid definitions, so valid computer programs, and others are not. And what this prefix tree does, so I have in this tree somewhere my valid definitions. I don't know, maybe these ones define something, the other I don't. And in this tree, if you have a valid definition somewhere, you always know that there isn't any valid definition below it in the tree. That's what prefixing means. Because once I wrote a dot, there isn't another definition that would be a continuation of this one. Or there isn't another algorithm whose description would be a continuation of the description of this algorithm. So this is really something harmless. But thinking about this like this tree, it's really helpful to understand which sets have zero and which has positive measure. So I would like to show you now, so I will stop now. I will not prove this theorem. First, I would like to show you something that I proved. And this is a proof that I really, really love. And you will see why. So what do I prove? So this is my claim. Every set in R has global measure 0. So okay, this won't be a correct proof, but never mind. It will be an amazing proof. So how do I prove that every set in R, let's just put here the unit interval. Every set in the interval has global measure 0. So here is really a fascinating proof of this using prefix tree complexity. So let's look at all these nodes that define something. And I have a natural measure on this tree. So the left half of the tree has measure half, the right half of the tree has measure half. And then in each step you split the measure into 2 equal parts. So this defines the usual standard measure, really the only one you would ever look at. So let's look at this nice measure. And then when I have a node, so I look at how long this sequence is, and the things below it, so the measure of this was a sequence X, and the measure of the part of the tree below it is really 2 to minus the length of X. And since I am prefix free, all these sets are pairwise disjoint. And their total measure is at most 1. So 1 is an upper bound for summing all these measures. So it will be an upper bound for summing the lengths of the computer programs that define something. So this will be an upper bound. I hope you all agree. And what do I know about KQ? So that I had a Q is a diacube, so now we are in R. Q is a diacritic interval, and KQ is its complexity. So what we always know is that if a cube has length n, we are in dimension 1, then KQ is at most n. But actually for most sequences, so for almost every x, we can say something a little bit better. So for almost every x in the interval, we can improve this slightly. So how do I slightly improve it? So that was the proof that the complexity of a sequence is at most its length. So if I have a sequence, I can always say, actually there was a constant here, so n plus constant. So why was this true? Because I can always say that its digits are 0, 1, 1, 1, and 0, and 1, and this will be a sentence whose length is only n plus c. But for almost every, so if you take almost every x, that's really the same thing as you take a random sequence of zeros and ones. Those that are not random, that's an answer. So for almost every infinite sequence, or actually for almost every sequence long enough, most sequences long enough, there will be somewhere a path which is just, say, constant 0 for a while. So you have something 0, 1, 0, 1, 0, 1. Then again you have something. But if this sequence has, say, length 1 million, it's very likely that somewhere you will see 10 zeros next to each other. And this is really a true statement, a trivial statement in probability, that yes, you will have in a random sequence long sequences of zeros. So if I want to describe this sequence with some precision, I can actually beat this a little bit, because say here I had 1 million zeros. Then I can just say that its first digits are and I just list them 0, 1, 1, 1, 0, 1, 1, something. Then there are 1 million zeros. And then 1, 1, 0, 1, 1. So the length of this sequence is not the length of this, but the original one was. It's a little bit shorter, because of course I don't need 1 million digits to say 1 million zeros. So depending on a million, there's a constant, and I just shrink the length of this sentence by that constant. So what this shows is that for almost every x, for an arbitrary large constant, an arbitrary large c, and for almost every x in the unit interval, there is some cube. So if I take a long enough initial section of my sentence, there is a cube containing x such that the complexity of the cube is not really its length, it's shorter than the length by this capital C. So k cube is at most the length of Q minus this constant. But I can always shrink it by a constant by finding 1 million zeros. So now what happens to our formula? So if I just sum this for these cubes, those cubes will cover almost every x. So let's look at this sum and use this. So what does it say? It says that 1 is larger or equal than sum. I'm simply summing the lengths of all these cubes. Sorry, by this I meant 1 over 2 to the n. And everywhere I did this elsewhere. Yeah, this is an n. When Q has size 1 over 2 to the n. So what you get is 2 times, this is not the mistake in the proof. This part will be correct, so I hope. So this is really what you get. C was a positive constant, then actually this will be a positive constant. It will have a plus sign. So these are cubes that cover almost every x, and Dirichlet intervals, and the total length is at most 2 to minus c. And I can do this for every c. So I have just proved that the unit interval has measure 0. So that's one of my favorite proofs. It's something I'm extremely proud of, that I found this. And I must admit, I was staring at this proof for a long time, and I had no idea what was wrong. So now the next homework exercise. This is the next homework. What is happening? So did it really prove? Probably didn't. I mean, I never had any doubt that the interval had positive measure, but the question is, where is the mistake in this argument? So let's leave this tomorrow. I want you, all of you, to have some fun and think about this. I want anybody to answer this loudly at the moment. And this also, unfortunately, means that we have to postpone this proof tomorrow, because in this proof, we do the same but correctly. So you will see that proof tomorrow. And now I would like to change gears and speak about something completely different. So I will speak about the Fürstenberg problem. So let's postpone everything about optimal occurs and about this beautiful proof to tomorrow. And I will speak about Fürstenberg. So I assume that in this audience everybody knows what the Cocker problem is. So Cocker set is when we have a set in Rn that contains a line in every direction, and we ask whether it is full dimensional, which is hard enough if the dimension is big. And the Fürstenberg problem is something which is even much harder. So the Cocker conjecture is easy in the plane. It was recently proved, and it's hard in R3, and nobody knows what happens in higher dimension. Fürstenberg is a generalization of Cocker, which is already very hard in the plane. And it was a famous open problem until like a year ago, or 1.5 years ago, and finally it was proved. So here is the statement. So something is here's the definition. ST Fürstenberg set So what is this? It's a three-dimensional set of lines. And each of them contains an S-dimensional set of points. So when I say t-dimensional set of lines, I don't mean that the union is t-dimensional. I mean, in the space of lines, this is a t-dimensional subset of the space of all lines. So if you want, you can write a line as y equals ax plus b. So you identify a line with the pair AB, and then you ask, what is the dimension of all the pairs AB? This will be this T. And then what was a conjecture, and now it's a theorem. So this Fürstenberg set always have Hausdorff dimension in the plane. So F is a Fürstenberg set in the plane. Its dimension is always at least the minimum of S plus 1. S plus t, and 3s plus t over 2. So there are really three cases, depending on which one is the smallest. And it was known before that if this is true, then it's sharp. I mean, there were examples showing that this is the best possible, but nobody knew whether this was true or not, until things started moving, like about 5 years ago. So now there are a list of papers. Let me tell you a little bit about the history. So in 2020, this was Neil Lutz and Don Stuhl. So they solved the case when T is less or equal to S. And of course, as you can guess from the names, using complexities. And then very soon after, this is 2021, Cornelia Hera and Pablo Schmerkin. Remember the last name? Yavikori? Yes, thanks. So they did the same without complexities. Same statement, when T is less or equal to S. And then in 2024, Hu and Ren, they solved it when S plus T is at least 2. And also in 2024, the same Ren and Wang finished the proof, so they did the remaining case. So this is S less than T less than 2 minus S. And then building on this in 2025, the same Wang and Zal, they solved Kakea in R3. That's the current list. And of course, as you can guess, today I would like to explain you this paper. So how to use complexities to show the Fürstenberg estimate when T is at most S. That's the plan for today. And again, I will show you, I will start with a wrong proof, but this will be a proof that is, on a deeper level it is correct. So first I will show you an argument which is not correct, and then my aim is to understand what we need to do to make it correct. And this really this is about what is called mysterious vector field. So let me start with the proof which is not correct. And for simplicity, such that it's easier to follow what is happening, I will, instead of an ST Fürstenberg set, I will just do it with S and T are 1. So that's like a Kakaya set. The Kakaya set is a 1, 1, or at least 1, 1 Fürstenberg set. And when you look at this formula, which unfortunately I have just deleted, the Fürstenberg conjecture, of course, says the Kakea set has dimension 2. And it's a sharp statement, so it cannot say anything else. So I will show you that the 1, 1 Fürstenberg set has dimension 2 first, and then I will also show you what to do in the general case. So let E be a Kakea set in R2. How do we prove that it has? How we prove that it has dimension 2 using complexities? So here is a really simple proof. So it relies on a theorem which we did many years ago. So this is with Giovanni Alberti and myself and David Price. So what we proved is that every Lebesgue set, so E is now Lebesgue set, E has what we call a mysterious tangent field. And I won't write down the full definition of the tangent field, I just write down the corollary that this proof will be using. So the statement is that for every x in E, we can choose a line call it Lx containing x, so through x, such that for every line and for almost every point in the line, L is Lx. So what this really means, think of a Kakaia set, it can have lots of lines through one point. Actually, there are Kakaia sets that have continuum lines through each of its points. And what this thing does, you need to choose, so you get a point, you see these continuum lines, you're allowed to choose only one of them. But you have to do it in such a way that along each line, at almost every point, you chose that one and not one of the other continuum. So this is surprising, but there is nothing wrong about this. This is a theorem. So I told you I am showing you an incorrect proof. This is correct, that these things exist. And now I will combine this statement with symmetry of information. And I get a proof that the Kakaia set has dimension 2. So let's see how to do that. So this will be, actually, won't be a full proof, it will be a sketch of a proof, since it's anyhow wrong, so I will ignore something. But it won't be wrong because I am ignoring something, it will be wrong for another reason. So by symmetry of information.
Marianna, can you hear me?
Yeah?
Can you please repeat the statement of the theorem?
Of the tangent field. Yes, so if you have any set of measure 0, so that's your set E, for each point you can choose a line, one of the lines that goes through X, in such a way that for every line in the world, at almost every point, almost every X which is in E, the line that you chose was this line. So if you have for example, a Kakaia set, and through every point you have lots of lines, continuum many, you can always choose one of these continuum many in such a way that along each line, the line you chose was this one and not one of the other continuum many. So for every single line, it should be true. At almost every point of that line, you chose that line and not one of the others that may have passed through the point X.
Thank you, Marianna.
So I now look at these pairs of points and lines, and then by the symmetry of information, I can look at that is the dimension of X and L together. So I will now use L is really my Lx. This is the same dimension of X plus dimension L given X, and it's the same dimension of L plus dimension X given L. So I'm cheating here a little bit because if I want to do this correctly, I have to be careful which one is Hausdorff, which one is Peckering, what is happening. So let's just pretend now that all the lim-ims and lim-subs are actually limbs. This is, so every set that I look at have the same Hausdorff and Peckering dimension. And this is not the main problem. This is just it's an issue, but let's see what happens if every set has the same Hausdorff and Peckering dimension. Every set in this statement, how do we prove in that case that the dimension is 2? So I'm lazy, I just put there dim and I don't care whether it's Hausdorff or Peckering. And if I try to copy the proofs from yesterday, I can. So I can choose L such that, so first I put here an oracle, which is the, of course, it cannot be anything else. It's the Hausdorff oracle of my Kakaia set, and the Hausdorff oracle of my line set, and the Hausdorff, no, just these two. And then this will be at least, I can choose an L for which this is 1 minus epsilon. We have seen this yesterday, we can do this all the time. And once I have an L, I can choose an X so that this is 1 minus epsilon. So that's really the same argument as last time. Now what about these two? So remember, through every point x, I have only one line. I assume that L is Lx. So if I know x, I know L. So this is 0. Once I know x, I already know L. And I am done. So what I proved, something plus 0 is at least 2 minus epsilon. Dimension of x is 2 minus epsilon, 2 epsilon. So for every epsilon, I can choose an x which has this big dimension. Of course, this means that the Hausdorff dimension of my set is at least 2. So there is a serious problem with this argument. It looks correct, it looks very nice. So the issue is really this one. And I say that if I know x, I know L. So it's true, it is a true statement that through every point x, I have only one line L. But if I want to do this correctly, I have to look at scales. So what I really need is not to check what happens in the limit, but what happens in each scale, and then take the limit. And what happens in each scale, so for this statement to be correct, what I would need, if I know x with some precision, then I know L with some precision. If this were true, then everything would be fine. But unfortunately, this is very far from being true, because this mysterious tangent field is not even continuous. So you will have points very close to each other with completely different tangent directions. So there is no way how, if you just know a point with some precision, you would be able to tell what is its tangent direction with some precision. So that's an issue. That's a serious issue. This is why this proof is not wrong, not correct, it's wrong. But what I will try to explain next is that in this paper of Neil and Don, basically this is what they are doing it correctly. So they are constructing something which is very, very similar to a mysterious tangent field. But they do it, it's a bit different, and it's something that makes this proof working. So let's see how they do this. And again, first I just explain this for Kakaya, and then later I will show that the same argument also works with Fussenway. So now this will be a real proof. This won't be a wrong proof. So a complexity proof that Kakaya set has dimension 2. And step 1 is what you would expect in every proof. You have seen before proofs of the fact that the Kakaya set in the plane has dimension 2. Step 1 is looking at strips that intersect each other and understand how big is the intersection. So I have some line L and another line L prime. But now I didn't take the limit, I just look at what happens in a fixed scale. So I look at these lines with precision n. With some fixed n. So that's really the same thing, or almost the same thing as taking two strips of width 1/2 to n. So there is some algebra you have to do, but a dyadic cube in the space of lines that really corresponds more or less to lines which are inside the strip of some compact size. And so this is really a line L with precision n, and this strip is my line L prime with precision n. And now let's look at the angle between them, theta. And let's call this 1/2 to the n. About, I mean, always everything is after some multiplicative factor. Also, these are after some multiplicative factor. So again, it's some algebra that if I have two lines that meet each other, say, inside the unit square, then this M is almost the same as saying that L and L prime are the same on precision M, and then they are not the same. So the angle between two lines, this is really the same. L is equal to L prime with precision M. So with precision M plus minus a constant, and not if the precision is higher. So it's really how many bits of L and L prime agree at the initial section. And now what this picture says about complexities. So we look at the intersection of the two strips. And if I have two strips of diameter of width 1/2 to the n, this is my angle. I have a very good estimate for how large the intersection is. So this intersection, and this is what really Ervikager proved that, this intersection has diameter about 1/2 to n minus m. Now let's write down this statement using complexities. So I look at these two lines. The intersection point is x, so it's somewhere in this intersection. Now if I want to know what x is with this precision, so if I want to know with n minus m precision what x is, and I already know L with precision m, so I know one of the strips, and I try to find x. This is not harder than finding the other strip. So this is bounded by k and L prime given L. If given L, I know how to find L prime, I already found x. Maybe I could do better, but this is not personal. So this is really the same statement using complexities that the two strips has an intersection of this diameter. And now let's play with this formula. So, okay, I lost my notes, but I think I remember this. So I just copy it here because it will be a long sequence of trivialities. So what can I say about the right-hand side? So k and L prime given L. So this is of course less than k and L prime given L. But with precision, instead of n and n, this is n and m. Because here I have less information, so I need to do more work. And I also assume that L prime and L were the same with precision m. So this is really the same as just saying k m mn L prime given L prime. So if I know L prime with some precision, did I swap things? Yeah. I know the first m bits of L prime, and now how hard it is to calculate the remaining n minus m bits of L prime. That's what this formula is. And then by the symmetry of information, this is the same as k n L prime minus k m L prime. Because if I add these two together, by symmetry of information, I get the joint complexity of L prime with precision n and L prime with precision m. Of course, knowing L prime with a larger precision and knowing L prime with a smaller precision is the same as knowing L prime with a larger precision. And this was the same again, the first m bits agree. So this is k and L prime minus k and L. So this was then an estimate for the left-hand side. So let me write down the full thing. Kn minus m and x given L. This is less or equal Kn L prime minus Kn L. And I told you that I fixed that precision. I didn't tell you I choose a large enough n from the very beginning. And I also assume that m and n minus m are large. Otherwise, you get some priorities. So everything is so large that the complexities are already very close to their limit. They could be bigger, but they cannot be too much smaller than their limit. I assume that my indices are large enough to ensure this. And now let X be a high complexity point of L. So like L is a one-dimensional set. I know that something is true for almost every point. So I can do this if I choose a high complexity point of L. This will be about n minus m times, do I do this correctly? Yeah, just n minus m. N minus m times the dimension of the line, but the line is a one-dimensional set. And what I get on this side, there is this k and l prime. I leave it as it is. But here I use that this is already at least this dimension, or almost. So up to some small error, I can put here minus m times the dimension of L. There are some small errors I ignore in all these calculations, but they don't cause any problem. So if all the indices are large enough, this is very close to being correct. And if you want to, you can keep track of the errors, but I won't do that today. So putting this on the other side, Kn L prime is larger or equal than n minus m plus m times the dimension of L. This is the form I was looking for. And now, okay, so this is true under some assumption. So one of our assumptions was that X is a more or less random point of L. And the other assumption was that the indices are large enough. But as long as the indices are large enough, and X is a random point of L, this is true for every L prime. That's really the statement. Now I make one more assumption, which is actually not the correct one. I mean, I cannot always assume this, but let's see what happens in the case when I can. So this is true assuming that the dimension X given L, this is like 1. That's okay, but I also assume something which is sometimes okay, sometimes not. So what if also the dimension of L is strictly less than 1? Just a little bit below 1. And this you cannot always have. So all you know is that you have a one-dimensional set of lines. You know that the dimension is bounded from above by 1. But in principle, it could happen that all of them have dimension exactly 1. So there is no reason why you would expect that there is something which is strictly less than 1. And the argument I show you really uses it in an essential way that it's strictly less than 1. So this is something we will have to fix later. Let's not worry about this for the moment. So now I just check what happens if this is less than 1, and then later I will explain you what to do if you don't have this. So if this is less than 1, in that case, the left-hand height of this is larger than dim L. Am I right? N minus m plus m minus n times dim L, and 1 is larger than dim L. So maybe I miss an L somewhere, n times dim L. That's what I wanted to say. So provided that dim L is less than 1, this is always L. Just says that n minus m is larger than n minus m times dim L. And 1 was bigger than dim L. Sorry, I want here now strictly. Strictly is important in this argument. So if you divide this by n, and let's n go to infinity, what you get is that the dimension of L prime is really strictly larger than the dimension of your line L, which is something strange and interesting. So what did we prove? If X is a random point of L, and L happens to have dimension strictly less than 1, that every other line, at least lines which are in a small angle, because I also assume that M was large, every other line in a small angle have bigger complexity than what L does. So maybe I should write this down. If X is a random point of a line L, and, so this and is important, the dimension of L is strictly less than 1, then every other line has larger complexity. Every L prime has larger complexity than X, larger dimension. But you can also do this in a large enough fixed scale, larger complexity than L.
L prime through X.
Yeah, L prime complete. So that's the Mr. tangent field we're looking at, so looking for. Now for every point X, I have a well-defined unique line. Let's just choose the lowest complexity line through X. So this is how I define my mysterious tangent field. For every X, choose the lowest complexity line. Through it, containing X. So of course this won't work, won't really be a Mr. tangent field. For example, we need this assumption. But what is true is that if this happens to be less than 1, then indeed, at almost every point of this line, we choose this one. Because almost every point is a random point, and I cannot have really two lines that minimize the same thing, because this minimization was a strict inequality. So this thing, really for my X, uniquely identifies L. And that's the Mr. tangent field. And now everything is, okay, I wrote dimensions here, but if I did it correctly, I should have written the same thing on a fixed scale, and it's correct. And a fixed large enough scale so that the dimensions are almost Kn. And then I am done, because if I look at the same type of calculation I tried before, so this was dimension XL, this was both dimension of X plus dimension given X, and it was also dimension of L plus dimension X given L. So again, I'm stopping now. What I write by dim, I really mean Kn, and everything is true up to a small error. But this is random, so this is about 1. This is something, I don't know what it is, it's just less than 1. I assume that it was strictly less than 1. And now, so this was the problem before, this is no longer a problem, this really will be like 0. So why will be this like 0? I have to check that if I know X with precision n, I know L with precision n, that's fine. I did everything on a fixed scale. But to make things correct, I also need a computer program that finds L using X. And that's also fine, because let's just, I have my line L, sorry, I have my point X. And let's just run every program whose length is at most this. Only one of them will output an L that contains X. Because every other line has bigger complexity. So I just run every computer program whose length is, I am on a scale L, so whose length is at most n times, whose length is at most the complexity on scale n of L given x. I stop when I find that this is a number. I look at every number every program whose length is at most 100, and I will find only one line as an output of these programs that indeed contains x. And that's the L I am looking for. So that's why everything is now correct. And what this shows is that the dimension of x is at least dimension of L, I don't know what it is, plus 1. So that's something which is always correct, provided that the dimension of L is less than 1. If dimension of L is less than 1, and if x is a random point of L. So are there any questions so far? Yes?
Can we find many lines where the complexity is minimal?
No, because I proved it. For every other line R prime, the complexity was strictly bigger than the complexity for R. That was the key thing.
Yeah.
So the strictly part was important. Okay, so actually the proof is almost finished. I just have to make sure that the dimension of R, first of all, is less than 1, and secondly, that it's just a little bit less than 1. So this will be the next lemma. So how do we make sure of this? So if we have in our Cocker set some lines whose dimension is, if we don't have any lines whose dimension is 1 or bigger, of course I can find an arbitrary close to 1. And that shows that my Cocker set has dimension 2. But what happens if most of my lines actually have dimension 1 or bigger? Then, okay, so let's pick any line. So let L be a line, but its dimension is not less than 1, it's bigger. And then the trick is, let's add some information. So I will use some information. I will find an oracle, use some information that lowers this to be just below 1. And I want to do this in such a way that this drops down. So I want to put here an oracle E. I already had an Hausdorff oracle A, which I didn't write, but it's there. And now I want to add some additional information B. And I want to do this in such a way that the dimension of L, which was before at least 1, now it should become 1 minus epsilon. And I also want to find this B in such a way that it doesn't destroy this property. So if you just put there any information you want, you would expect that dimension x given L also dropped. But no, I don't want to drop that. So I want to drop the dimension of L, but I don't want to drop the dimension of x given L. If I can always do this, I am done. And my claim is that I can always do this, and it's actually not very hard. So let's write down the statement. So this has nothing to do with Cocker sets. This is a statement about complexities. So here is a lemma. So let x be now any finite sequence of zeros and ones. And let's look at its complexity. So that's a monotone function. And it has length n, so it finishes at some n. And at this point, it's k and x. But I want to drop this complexity, so I choose something below it. And I'm looking for an oracle. So this function was k and x. But now I'm looking for an oracle which doesn't go above this line. And actually what I will do, I will find an oracle for which I get this curve. Exactly. So this will be this thick curve. This will be complexity of n, complexity of x with my new oracle b. So that's one thing I want. When my complexity became too high, I want to drop it down. I want to add some information to these bits to make sure that it stays constant. I don't want to add any information to the first many bits. And we had this other property that x should remain random. So this will be one property I want. I want this picture. And the second property I want is that ky given x should be the same as ky given x using the oracle b. And this should be true for every y, absolutely every y in the world. So the lemma is that such a b exists. There is a b for every horizontal line below k and x. There is an oracle b such that this holds. I will have exactly this picture, no error estimate, or maybe some extremely negligible ones. And this will also stay exactly the same, or maybe some extremely, actually, there are always some logarithmic errors everywhere, but I won't introduce any new errors. So once I can do this, the proof is finished, because I just put this b, this 1 minus epsilon will be my horizontal line, and I have just found a point in my cocktail set whose dimension is at least 2 minus epsilon, and I can do this with every epsilon. So how to prove this dimension of lemma? Once we did this, we are done with the cocktail set. So I can delete this. Actually, there is a very simple way of saying what this oracle b is. I will just define b. Here's the proof. So let's look at this picture. Let's look at where it hits this line. So to simplify notation, I will introduce a new letter. So this thing was here x, and I will call this y. So y is an intersection of x. I'm sorry, I already had a y. That's a z. And this is my y. I shouldn't mix these things up. So again, things are not exactly exact because actually this complexity is not a continuous function. It was just defined on integers. But we connect it with a curve and choose something where they almost intersect. Connect it with a piecewise linear function. So let's suppose that we are y, and our aim is to drop everything down to ky. So this height here, that's ky. So let's look at how much information I really need to calculate x if I already know y. I don't know how big or how small it is, but there is a computer program that does this. So let P be the computer program. Whose output is kx given y, the value of x k given y, and not just any computer program, but I want the shortest one, of course. So I want the length of p to be equal to kx given y, and yeah.
The output of the program to be x, given input y.
Say it again.
I think you want the program to be the
You should output x with the information y, right?
Yeah. The output is x, and the
Yeah,
given
okay.
y.
Okay. But I still want this. The length is. I choose the computer program that does this. It finds x given y. Yeah, that's what I should say. That be the computer program that finds x given y. If you already know y. And again, there can be several ones, but actually I can find the first one. So I just run every computer program of this length, and I choose the first one. I stop when it does this. So that's an important thing. P is computable. I know what P is if I know what X is. If I know what X is, I know what Y is. And then I just run every computer program of this length, and I choose the first one. So P, what P is, that follows in a computable way from what X is. And the oracle I'm looking for is actually just P. Put P equals P. So this is a string of zeros and ones. And usually an oracle is a Cantor union of strings of zeros and ones. Now this won't be a Cantor union, this will be just one. That's okay. And it's actually very helpful because I don't have to worry whether I put my oracle in an upper index or I put it here. It's just a finite string of zeros and ones, and these both mean that I just know what P is, every digit of P. And really my claim is that this P, as an oracle, does exactly what I want it to do. So it changes this graph to this one, and it also has this second property. So let's see why. So the first thing to notice, so why is this part flat? Because if I already calculated Y, and I know what P is, so I'm looking at, now, Y is this function K X given P. So if I'm already at this point, I calculated Y and I know P's, I don't have to add any more information. I can just run my program P with the input Y, and I will find X. I will find all the remaining digits of X. So if I already have Y and P, I also have X. I don't need any extra information for that. So that's why nothing is happening after Y, provided that you have P. The complexities won't change because you don't need any extra information. If you already calculated, if you already know everything about Y, and you know P, then you know everything about X in a calculable way, because the program that does this is just run P using Y. So that's why this part is flat. So really, P gives every information I want about these digits, but I also have to check that it doesn't give any information about Y. So why is that? So we need to check that the complexity of Y is the same as complexity of Y given P. If I know P, so in principle it could be smaller, but it's not. If I know P, that says nothing about Y. That's really the claim. So why is this true? Actually, there's a very simple argument why this is true. So look at the left-hand side. What if I add Kp to it? So what if I have both Y and P? Then I already have X. So, and this height becomes something larger than K, larger or equal Kx. And for this one, what am I doing? If I add, no, I wrote it in the wrong side, sorry. If I add Kp to this, so I have Y, this is symmetry of information, it's K, Y, and P. And if I have Y and P, I also have X. So this is at least Kx. Now for this side, to get Kx, what I need to add is Kx minus Ky. Then I get Kx. And now if you look at this formula, come back to this, but first let's look at this one. So this size is, so the length of P is an upper bound for the complexity of P. And this one, so it's the same thing we have seen before. I have a string. In order to calculate the whole string knowing part of the string, this is kx minus ky. So what was happening here? Here I added something larger than here to get the same thing. Then this must have been smaller than this, or less or equal. So this argument shows, since I added to ky something larger to get kx than what I need to add to this to get something, at least kx. Therefore, I have this inequality. The other inequality is always true. So that's the end of the proof. So what this proof really does, so first of all, we had this intersection of strips, which we always have when we prove something like the cocktail set. And then we showed that actually choosing the lowest dimensionality line solves everything, provided that we can drop the dimension below 1. And without, sorry, I forgot to check this one. So what is this? Okay, so we also need to check that will be nothing. We need to check that k z given x is the same as k z given x and p. But that's okay, because knowing x is exactly the same as knowing x and p. If you know x, you already know p. P was defined by x. So this is okay. Knowing x is precisely the same as knowing x and p. So then you can do anything you want. Okay, so there was these two lemmas: the intersection of the strips and how to drop the complexities if they are too high. And then there was trick with that I call the mysterious tangent field. It's not, but it's somehow it's a version of it. It's a mysterious tangent field on a fixed scale. Now you take limit, so that it's still discontinuous, that it's continuous on that scale. And the discontinuity comes from the fact that the two scales may not be compared to each other. So as you go into lower and lower scales, these tangent directions may be rotating. And they may not in the limit. So you don't get a tangent field in the limit, like we had with Giovanni and David, but it's defined on a fixed scale. And it also has the big advantage, which I like, that you can just say what it is. Choose the lowest complexity line. With Giovanni and David, we never really saw how to choose the tangent field. We had a construction that did this, but we were always, at least I was always puzzled about, okay, but how do you find it? If you just look at a point x and how the set looks around it, it's a local property, and somehow our proof was not a local thing. This is very local. I am sending at the point x, I just look at all the lines through it. I don't care what the set does on other lines. And I choose the lowest complexity one. Okay, so that was the proof for the cocktail set. Now let's also do Fürstenberg. I still have 10 minutes, and that's more than enough. So I am basically just claiming that the same argument works to get to what they prove. So first, let me write down what they prove. So this is the theorem of Nilutz and Don. So this is in R2. We have a point in R2 and an arbitrary line. An arbitrary point and an arbitrary line, but the line contains x. And then the claim is that the dimension of x is larger or equal to the dimension of x using L as an oracle, plus the minimum dimension of X, the same thing, dimension of X using the oracle L, or whichever is smaller, dimension of L. So this has nothing to do with the first submax. So this is a statement about points and lines in the plane. For every point and every line that contains the point, they claim that this inequality is always true. And first submax has a corollary. So if now these are points of an ST first submax set, then you can choose this to be like larger than T minus epsilon. You can choose this to be larger than S minus epsilon. This is a T minus epsilon. S minus epsilon. So a corollary of this theorem that for if F is an ST first submax set, then the dimension of F is always at least S plus the minimum of S and T. So this is always true with S and T. It's unfortunately not optimal when one of them is larger, but it's optimal when it's smaller. So the statement I wrote down like an hour ago is the case when this is sharp. The other case is also true, but it's not sharp. But this is really the corollary of this theorem about points and lines. So how to prove this theorem? So I will more or less just copy what I have just did in a Kaggle proof. So I want to drop something, of course. I fix a large enough scale n, large enough m, large enough everything. And I will look at this thing here on that scale. And that's the thing I will want to drop below. So here is the proof. So choose a large enough scale. And choose an, a times n, just below this minimum on scale n. Whatever it is in that formula. And drop that. So in this formula I had K and L. So now complexity of L is now bigger than an, and I now drop down the complexity of L to an. So that's the next step. Choose an oracle, choose the oracle like before that drops K and L to an. Okay, and I know that the other term was also at least an. So I will actually denote this by, on that scale, by an plus bn, and then b is something strictly bigger than 0. Because an was strictly smaller than 0. So the next thing is do the intersection of shapes. Intersection of strips arguments. And then what you get is that for every line R prime, K and R prime is larger or equal, this was K n minus m n x given L plus K and L, but now using our oracle, that drop the dimension. So how large is what? So this here, since my scales were big enough, and so what I am really trying to say, this was like a plus b times, that's my dimension, a plus b. So what I expect is that this is like a plus b times n minus m. at least, because everything is already at least the minimum. And what about this one? So this is an M. It's not N, so it's not the thing I dropped. It's that either this putting this oracle P here, either it dropped down to AN, or it remained what it was before. So this term here, this is either AN, A times N, or it's equal to the same thing without the oracle, KML, which again, since my M is large enough, this is at least M times A. So A times N is even bigger than A times M. So this term here is at least A times N, always. So K and L prime gets rid of this term A times M in this formula. So K and L prime is at least A N plus B times N minus M. And remember Kn, did I write it? So Kn, not L prime but L, using the oracle, that was An. That's what I dropped it to. So again, this is strictly larger than this. It's larger by this term B times M minus M. I have exactly the same thing as before. Every L prime has a strictly bigger complexity than the complexity of my L. Everything is all the time computable. I can use the same trick as in the first wrong proof with the Mister's vector field. And the conclusion of all these things will be, let's write it down. So I have this Kn which is now the same as Kn X and L, because this is symmetry of information using the fact that L given X is 0. And so there is another term here that it's 0. And it's also the same, but I'm saying X, yeah, it's minus 0, never mind. So this is K and L plus K and X given L. And this is An. And this is like, that was it. The dimension of something like this. So if X was random, then so if you do this correctly, which I mean, I'm not doing now it's correctly, but yeah, I do, because I want a lower estimate, and this is larger than if I put X into the oracle. So it is correct, it just makes it better. And then what this proves is that when you divide by n and so on, what this proves is that the dimension of X is at least A plus the dimension of X using L as an oracle. And there is also the oracle P. So that since this is true for every A which is just below that minimum, it's also true with the minimum. And then you really get the dimension of X is larger than this term plus the minimum, which is the same as before. The one below. Then we choose An to drop below. That was in the formula of their theorem. And the proof is free. So that's the proof of this first step in the sequence of papers proving Fürstenberg's conjecture. So I have 1 minute left. I hope you can still hear me. And people are there.
Yes, yes.
Okay.
We are here.
So I have a strange request. So next time I will tell you why it's not true that every set in R has measure 0. Of course, I will have to do that. But then I think it would be a good idea if I ask Don to speak about anything he would like to speak about for the remaining lectures. So I don't know what it will be, but he's a very good speaker, and he has lots of good things to say. So I think this is a good plan, that there is no reason why I should stand in front of him and speak about his results. And maybe he could give most of the next lecture.
Yes, of course.
So I will take a little time at the beginning showing that the unit interval have measure 1, but other than that, so he may speak about optimal R-close, he may speak about, I don't know, Marston projection theorem or distance set, or I'm sure it will be something interesting.
Okay.
But let's leave it, let him decide.